Okay, everyone, it's 1 o'clock. Welcome back. Sure, we all had a wonderful adventure last week, and I'd love to hear your stories, but not today. Okay, we've got a lot of ground to try and make up, so we're going to get right into this. We are scheduled. Well, I sent an email saying that I'd like to have the test that was supposed to be last Thursday. I'd like to have it this Thursday. So how do y'all feel about that? I mean, I think I gave you a review like a long time ago, so you've had plenty of time to work on that. And so I think if we just keep it for Thursday, then it'll just cover that material, and whatever we cover today won't be on the test. All right.
Sounds fabulous.
Great. So what I just want to be clear. Okay. So on Thursday, you're going to come into the Zoom session. And then when you're in here, I'm going to send everybody a link through Dropbox. I'm sorry, a link through the chat to go to a Dropbox, and you're going to go grab the exam from there. At that point, I'm going to give everyone about 10-15 minutes to write all the problems down. And then I will officially start the test, which means you'll have to get your camera set up in a way that I can see your entire workspace. This first time through, it's going to be a pain in the ass because there's going to be people who aren't setting up their cameras properly, and you know, just be prepared to be patient with people. And you know, what I recommend is that you use your phone to log into Zoom, and that way you can set up your phone somewhere in your room so that you can really just show me your workspace. I've shown you, I think, a picture in the orientation, but I need to see you. I need to see you. I need to see the desk, and I need to kind of see what's in front of you. So you're not allowed to have your computer on or anything like that during the test. You can just have your camera going. So then you'll take your test, and as soon as you finish the test, you're going to have to either scan it or take pictures and then send those pictures to me, and I'll give you a link to go send that file to me. And remember, it can't be 10 different pictures. It has to be a single file. So I think I've given everyone an opportunity to practice that. Again, this first time through, we'll see how it goes. But if you come in here and you don't have your camera on, you can't take the test. If you can't get your camera set up properly, you can't take the test. Right? So I need to be fair to everybody. So I can't have one student who, you know, has their camera just on their face and that be okay. All right. Everyone's got to have level playing field here. Any questions on that?
Do you know if Zoom can run in the background of your phone? Because I have cam scanner on my phone, and I might have to like close out the Zoom thing to send you the file.
Yeah. Okay, so good. I'm glad you brought that up. So what'll happen is when you're done, right, you will, you know, go grab your phone, and you'll just, in the chat, you'll just send me a message saying I'm done. Okay. As soon as you say you're done with the exam, then you can log out. You can close the Zoom session out, and you can leave, and then you can take pictures and do that. And I'll give you about 10 minutes, 15 minutes to get me that file. Okay. So there will be 10 or 15 minutes that you'll be unaccounted for. All right. And that's the time you have to get the pictures taken, everything into one file, and then sent to me. Does that make sense, Brian?
Yeah, we just send it to your Canvas.
No, I'm going to send you an email, and it'll have a link to a Dropbox, and you'll just upload your file to that Dropbox link.
Okay.
Okay.
Would we be able to print out the test, or would you rather us write it out?
If you have a printer, you may print it. It's just, I know not everybody has a printer, so I can't require it. So that's why I have to give everyone 10 or 15 minutes to write down the problems.
Got you. Thank you.
What were you saying about the test? Because I just got in.
The test is on Thursday. So I'm not going to repeat everything I just went through. Just when I upload this video of this lecture to YouTube later today, just go watch the first 5 minutes. Because I think I covered a lot in the first 5 minutes, right?
And 2.1 is going to be covered on the test too, right?
Yes, part of 2.1, not all of 2.1. part of it because we didn't finish it. So we need to still talk about 2.1. The review shows you how far you need to go. If you look at the review, like that's where the material will stop. Any other questions?
No.
Okay. So in the just so you know, in the event that you can't get your camera running or you're not setting things up, I'll probably lock you out of the meeting so you won't be able to be here. And then I will give you an opportunity, if something happens this first time around, if something happens, I'll give you an opportunity to make up the test. But there's a catch to it. You cannot get a grade higher than the lowest test score. So you can't, no matter what you do, like if you retake the test 2 days later, the highest score you can get is the lowest score of the people who were here. All right? That sucks. You don't want that. Okay. But I just want you to know it won't be a 0 this first time through. All right. Unless the lowest score is a 0. But I'm pretty sure people will do better than that. So don't freak out about it. We'll get it taken care of. Just make sure that you can get your camera set up. And I recommend that if you're going to use your phone, which I expect most of you are going to do, that you have a charging cable plugged into your phone during the test so that your battery doesn't run out in the middle of the test. I don't mind if you listen to music in the background or whatever. That's fine because I'm going to have everybody muted. But I might say something to the class like in the middle of the test. So you are responsible for being able to hear me. So if I say, hey everyone, because I do some things during the exam that kind of keep the integrity of the test. I will probably 3 times during the exam ask everyone to write like a word down, like, I don't know, calculator. I'll say, write the word calculator on your test and show it to the camera. And then that way, when you submit your work, I know that it was your work because you wrote calculator on the test and you showed it to me. Does that make sense? Instead of your friend who's an engineer who's taking the test for you in the other room. You know what I'm saying? So I have all these little things I do. So you just have to be able to hear me during the test. I'm trying to outsmart the clever people who don't want to be honest on this test. I always tell my classes, it's not that I don't trust you, okay? It's just that I don't trust you. So, right, someone in here is probably going to try and do something. So, just got to make it fair, right? It's all about fair. All right, I need to shut up. We're gonna get down to business. 2.1, here we go. Okay, so the main idea from the end of last class, which was so long ago, right, was that we had some function y equals f of x, which is the green function here. We go to some arbitrary point A, we go up to the graph, we draw a dot there, and we are trying to find this tangent line. And so we have a formula. Well, we actually have kind of 2 formulas. The first formula that we have is this one right here. And what that formula gives us is the slope of that blue line, the slope of it, the pitch of it, right? And it's a limit. You have to take the limit as x approaches a of f of x minus f of a over x minus a. And we went through that, and I tried to show you how we came up with that formula. And I hope that you were convinced of it and you're happy with it. But all that does is gives you the slope, right? The slope of the line. Now, the other thing that we may want to determine is not the slope of that line, but the equation of the line. And that's a college algebra question. What's the equation of a line? So we use a formula from college algebra, the point slope formula. And all we do, let me write the formula down here below it. It's y minus y1 equals m times x minus x1. This is called the point slope formula for a line back in college algebra. We're just going to use that formula to find the equation of the line, except that the slope we're using is not just some random slope. It's the slope that we found up here with the tangent line, with the limit. So in order to use this formula, all we need is the slope, which we have to calculate. And then we need a point on the line. We need an x1, y1, which is always going to be that point right there, x1, y1. Whatever that point is the point we're going to plug in to that equation. So since it's been so long, I thought it would be useful if we do an example and then we'll get into the new stuff. All right. So as an example, would y'all like me to do one of the problems on the review? Or
Sure.
Yes,
Yeah.
other than the review? The review?
the review.
Okay, let me bring up the review. So here's the review. What do you think? That one?
Go ahead and pick the hardest one on the review.
Well, you know,
Air
these
quotes.
number 14 and number 13 both have their own sort of algebra challenges. You know, this one has a certain algebra challenge. This one has a different algebra challenge. They're both challenging, but they're different. So what do you want? You want to do 14?
I was thinking maybe the one with the square root, just because I don't know. I get kind of confused. I don't know about how everybody else feels
Okay,
about square roots or not. Or
I'll do this one. Okay, so let's do this. I'll just start a new page. All right, so what we're being asked here is to find the equation of the tangent line to this curve at a certain point. Okay, so I don't even care what the graph looks like. All right, I don't care what it looks like. All I know is that if you go to 1 and you go to 3, 1, 3, this point, right, that point is on my graph. Who cares what the graph looks like? Okay, that point is on the graph. And what I'm trying to do is find, there's a tangent line to the graph there. And I'm just totally guessing right now what it looks like. Okay, there. And what we're trying to do is find the equation of that line. All right, that's what we want. So the first thing we need is the slope of it, right? So to find the slope of the tangent line, I need to take the limit as x approaches a of f of x minus f of a over x minus a. That's the formula, all right? Now, I'm not providing you that formula on the test. Remember, the only formulas you're allowed to have are the ones that are on Canvas. So if you go to Canvas and you go to our main page, let me bring this up. Hate having to log in again. These, I told you very early on in this semester that it's up to you to go print out these formulas. So hopefully you have these. If not, you have to hand write all the formulas before the test. Don't come in without them. So you go to files, you go to, where is it? Formulas right here. So you can have all 6 of these sheets. Okay. And then you can also have the limit summary. I will allow you to have that on the test for this first test. All right. But that's it. That's all you're allowed to have. So that means that you need to know this formula. All right. So now the question is, what is A?
Isn't A
the
the
coordinate
y?
or y?
The A is the X coordinate. It'll be the X coordinate that we're looking at. So that's 1, right? That's where we went up. So A here is 1. So I'm just going to rewrite everything. This is limit X approaches 1 of f of x. I'm replacing all the A's with 1. Okay, so now I need to figure out what these things are. So let me figure out, first of all, well, this part's easy, right? F of x, I know what f of x is. It's right here, right? So let me just write this again. Notice I'm writing the limit again. So f of x is the square root of x plus 8. Okay, then I'm supposed to go minus, and now I need to figure out what f of 1 is. So that means all I'm going to do is plug 1 into the function, right? And so when I plug 1 in here, I get 1 plus 8, that's 9. Square root of 9 is 3. So that's going to be 3 there. Any questions on that? Where I'm getting 3 from? No? Okay, the bottom is x minus 1. Okay, so now we have a limit problem. All right, now we've basically got this down to a limit. And if you take the limit right now, if you try it, you're going to get 0 on top and 0 on the bottom, and that's bad. Right? So we need some algebra. So what sort of algebra comes to mind when you see something like this? Anyone?
Conjugate.
Conjugate, yeah, because square roots, right? So when you see square roots, conjugates seem to be the way to go. At least it's a road you can go down, right? So I'm going to multiply the top and bottom of this by the conjugate, which is square root of x plus 8. Instead of minus 3, I'm going to do plus 3, and then square root of x plus 8, and then plus 3 on the bottom. And I'm just going to slap those in parentheses. And then I'm going to slap the numerator over here in parentheses. And I'm doing that because I have to FOIL out. I have to FOIL out the top. Okay, so when I FOIL this out, good things are going to happen here. This root times that root, the root goes away. I'm just left with the x plus 8. The middle terms I ignore, right? I don't have to worry about the middle multiplications. That's the whole point of the conjugate. So really, I only have to worry about this. -3 times +3, that's -9. And then over, and I've said this several times, but I'll say it again. On the denominator, do not multiply that out, okay? You want to preserve the x minus 1. You don't want that to go away. So we're just going to leave it just like this. So it's the x minus 1 times this. All right. Now what we're hoping for is that the x minus 1 cancels. And I think you can see right here, things are going to be nice. This up here is x minus 1, isn't it? X plus 8 minus 9. And that's good. Life is good now because this x minus 1 factor cancels with that one. And so we're almost ready for the limit. The limit as x approaches 1. Okay, what's still in the numerator? Everything's canceled out, but what's still there?
1.
Gotta have a 1 up there, right? So there's still a 1 up there. And then the denominator is just the square root of x plus 8 plus 3. And now at this point, we can let x go to 1. And if you let x go to 1, you don't have to write the limit anymore. You're going to have 1 on top. And then we replace that x with 1. So it's going to be 1 plus 8 is 9. So square root of 9 plus 3. But the square root of 9 is 3. So you get 1 over 6. I almost multiplied them. 1/6. All right. So here's what I can tell you. That if you were to look at the graph of this function, and you were to go look at the tangent line at that point, 1, 3, that the slope of it would be 1/6. Now, 1/6 is a positive number, so it would be sloped up. I don't know, how does your camera look? This way. Okay, so
Yeah.
from left to right, it goes up. Okay, from left to right, it goes up a little bit. I mean, 1/6 isn't a very big slope. But we're not done because we wanted the equation, right? The equation of the line. Please, on the test, don't get me the slope and stop. If I ask for the equation, you need to go the rest of the way. So you wouldn't get full credit if you stopped at this point. Okay, so now I'm going to bring in the equation that I need, which is y minus y1 equals that slope of that tangent line, and little subscript, that subscript tan just means it's the slope of the tangent line. Then x minus x1. Now we know all the numbers, right? What's y1 and what's x1? So y1 is what?
What is it? The 1 and 3 guy over here.
Yeah. So the 1 is the x1 and the 3 is the y1. Okay, so we're just going to replace those. So this can become y minus 3 equals the slope, which is 1/6. And then x minus 1. And I would take that as an answer right there. If you want to solve that for y, you can. Okay, if you want to add 3 to both sides, you can do that. All right. You could even distribute the 1/6 through if you wanted to, but you know, all I want is the equation of the line. As soon as you plug in those numbers, you have the equation.
So just a quick question.
Yep.
We use that y minus y1 equals m10 x minus x1 to find the equation of a line.
Of the tangent line, yes.
Tangent line.
Mm-hmm. So I'm going to do this right now. Here's square root of x plus 8. That was the original function, wasn't it?
Yes.
And we went to the point, let me see, we went to the point 1, 3, which was that point right there. And we tried to find the equation of the tangent line, which we found to be 1/6 x minus 1 plus 3. Do y'all see we got it? Do y'all agree that that line looks like it passes through that point and is tangent to that curve? So it kind of goes, just touches right through that point. Make sense? Okay. All right, so what is today about then? Well, today is about giving you another formula to do this. So when I first introduced you to this idea, it all came from this concept of we're going to take a graph, we're going to pick some point, we're going to pick a second point, we're going to draw a line, and then, oh, that's not the right one. First point, second point, draw a line, and then we were going to move that second point closer and closer to the first point, and that was the process of taking the limit. This is us letting x approach a, okay? That's what we started with when we started this section. We're going to do the exact same thing now, just using different notation, okay? It's just different notation. So here's how it's going to go. Start with a blank sheet here. So instead of me doing this, okay, this is what we did before. We picked a point A, then we picked a point X, and then when we did the limit, we let X approach A, and what that did was it slid that point X closer to A until these points basically became on top of one another, right? That was the main idea. Instead of that, I'm going to do this. I'm going to pick a point A. Oh, let me draw my graph again. So I'm going to pick a point A. And I'm going to pick a second point over here. But I'm not going to call it X. I'm going to call it something else. I'm going to call it A. Well, wait a minute, it can't be A, right? Because if it's A, then those are the same. They would be the same, wouldn't they? So I'm going to say it's A plus a little bit. So H is just some number. So I'm saying if this is A, then this has got to be A plus a little bit. Do you all agree? It would be, this point would be to the right of A because it's A plus something. So I'm going to put that point here. And now what I'd like to do is I'd like to see if I can slide this point over to here. So can somebody tell me what limit I would have to take to make this get closer to A?
Isn't it h does it approaches 0, right?
Okay, yes. So in this one, in order to let the x go get close to A, all you had to do is say, okay, let x go to A, right? And this moves over towards A. But here, to move this A plus H over to A, all I really have to do is make this H get smaller, right? If the H gets smaller, then that point starts to move towards A. So instead of doing limit as x approaches A, I'm going to do limit H approaches 0. And if H goes to 0, then this point moves to the left. Do y'all see that? It's subtle, but it's important to understand that in this limit, you're essentially moving this dot on top of that one. Yes? And then the rest of it is, the rest of this formula is just the same formula we just used. Remember the formula was this? I'm going to write it down over here. F of x minus f of a over x minus a. That same formula. So for us, we still have f of a, right? That's still here. What is f of x for us though? Instead of x, what are we using?
H.
A plus h, right? So I'm going to write f of a plus h minus f of a. Do y'all see that that's the same exact formula as this one, except instead of x, I'm putting a plus h. Yeah?
Yes, I see now.
Now on the bottom, instead of X, what am I going to put? So instead of this X, I'm going to put here what?
Right?
A plus H, right? A plus H. And then minus what?
A.
Minus A, right? Do y'all understand that?
Wouldn't it equal 0 over 0 eventually then?
Yeah, it will, but that's, remember, the limit will allow us to get around that, right? The limit will allow us to get around that. So please understand that all I've done is everywhere I have an X, right? I've replaced it with A plus H, right? So I replaced it there and there. That's it, right? It's the same formula, just a different way of writing it. Now, in the denominator, do y'all see what happens in the denominator?
It doesn't H end up just being isolated by itself, right?
Yeah, the A's cancel, don't they?
Yes.
This A and this A go away. So you'll always just have H down there. And this is the second version of the formula that gives you the slope of the tangent line.
Question.
Yes.
That it kind of looks like the difference quotient. Is that what we're kind of implementing, but making it calculus?
Yes. So in college algebra, you studied the difference quotient, right? This is the difference quotient from college algebra. And in college algebra, you had no idea why you were doing that. But now you see why, because we need to be able to calculate this and then take a limit. So in college algebra, you didn't do the limit part. All you did was this part. And that was just to make sure that you mechanically knew how to do it. So that when you get here, we're not sitting here having to, you know, first time you've ever seen it, you know, you have some background with this. Okay, so we have two formulas. Do y'all understand that? We have two formulas. Let me get down here.
I have a question.
Yep.
How do you know which one to use?
I was hoping you would ask that. Okay, so let me just point this out. Here we go. So right now we have two formulas that both give you the same result. They both give you the slope of the tangent line. Now I didn't write tan here, but just understand that that slope we're getting is the slope of the tangent line. You are free to use either one. Okay, so I don't know who asked which one we use.
Vivian.
Who?
Vivian.
Vivian. Okay, so Vivian, really it comes down to each problem can be easier or harder depending on which one you use. A lot of people, what they do is they pick one of these and they're like, okay, that's the one I'm always going to use. I would recommend that you do not marry yourself to one of these. Okay, don't be like, well, I only use this one. Be free to use both. But to be completely honest with you, the one that we are going to move ahead in the class with and spend more time with is going to be that one. All right. But like I said, the algebra is different when you use these formulas. Let's do the same problem that we started with today. That same exact problem, but let's do it with the blue formula instead of the one we did it with to start. Okay. That sound like a good way to contrast these two?
Yes.
Okay, let's do it. All right, so let's do this problem again. But let's use the other formula. All right, so everything is pretty much the same. We've got our graph. We went to 1, we went to 3. We know we have this point. We're trying to find the slope of the tangent line through there, right? We're trying to figure out the equation, sorry, right? So what's that equation? So first thing we're going to do is we're going to see if we can find the slope. So the slope of the tangent line is equal to, using the second definition, is limit h goes to 0, f of a plus h minus f of a all over h. I always think about this. I don't know why I think about this, but have y'all ever seen Kill Bill 2?
Yes.
Kill Bill with Uma Thurman. Okay, I don't know. It's kind of an old movie, I
it's
guess.
amazing. It's a fantastic
Yes.
movie.
Yeah, so in Kill Bill 2, Uma Thurman is training up in the mountains to, I guess she's training martial arts or something like that. And she's like training so hard that she's waking up in the middle of the night, like punching into the wall, because that's all she's doing during the day is like practicing punching. I always think of like people, my Cal 1 students, like waking up in the middle of the night, like saying limit h goes to 0, f of a plus h minus f of a over h. Like you just should get so comfortable with this formula that you're just like almost like saying it in your sleep. All right, because it's that big of a deal that you memorize it. All right. Okay, so I doubt that's going to happen, but
No, it has.
yeah. Okay,
Yeah.
good. All right, so here we go. We're going to do this now. Same issue that we had before. We need to figure out what a is, right? Like that's just the generic formula. So we need to figure out what a is. So a here is 1, right? We already know that because same a from the last time we did it. So this becomes f of 1 plus h minus f of 1 over h, right? So all I did was replace that a with 1 and that a with 1. And now we have to figure out what this is. And this is where things are going to get a little different. So what happens if we plug 1 plus h into this? That means we have to replace this x right there, right, with 1 plus h. We will get square root 1 plus h plus 8. Isn't that what we get?
Yeah.
Yeah. And then minus, now f of 1, that's okay because we just plugged 1 in there. We did that earlier and we got 3, so that didn't change. And on the bottom we have h. Maybe there's one more thing we can do before we go any further.
Conjugate.
I'll do that in a second, but let me do this. I'm going to go h plus 9 minus 3 over h. So do you see all I did was put the 1 plus 8 together and got a 9?
Yes.
Okay.
For really quick, when you had put f of 1, wouldn't we already know the coordinate wouldn't we already know that it's 3 because it's given to us, so we don't really even need to think about the math on that one?
Exactly. Yeah. If they give you the point 1, 3, then yes, in some way you already know what this is, right? Without having to do any math, right? However, what if the problem was phrased this way? Find the equation of tangent line at the point, and they don't give you the point like that. They tell you at x equals 1. So then what you would be doing is you'd say, okay, a is 1, but then they don't give you the y coordinate, right? So you then would have to do this part.
Yes.
That makes sense?
Mhm.
Okay. All right, so here we go. At this point, if you check it right now, I'm not going to do it, but if you take the limit right now, you will get 0 over 0. Okay, that's what would happen. So I think I heard Benjamin say conjugate. Did you say that, Benjamin? Someone did.
Yeah, he said.
Yeah.
Okay, good. So we're going to do conjugate again. So, I mean, this is very similar to what we did before, right? It's not real different, but it's still a little bit different. So I'm going to go here to here. Make sure I write my limit down again. Okay, the root goes away, I get h plus 9. And then I only have to worry about this part. That's going to give me minus 9, right? And then on the bottom, I'm not going to multiply that h through. I'm just going to leave it to the side of this conjugate. And do you all see what happens?
Yes.
Those 9s go away. And now you have an h on top, right? And you have an h out in front on the bottom. And so won't those cancel with one another?
C.
So first you get rid of the 9s, and then the next step would be to reduce the h's out. And so I'm left with a limit still. I'm not letting h go to 0 yet. I have a 1 on top, and I have the conjugate on the bottom. All right, now at this point, let h go to 0. So if this thing goes to 0, you get square root of 9, which is 3, plus 3, and you get 1/6 again. I'll stop here. You could get the equation by doing what we did on the last problem. We had the slope, and yeah. So what do you think? It was different, but I mean, in this case, not too different, right? Still had to use a conjugate.
So we.
I have a question real quick.
Oh, go
Yep.
ahead.
I kind of got lost a little bit where when we had the f of a plus h and how we got it to square root of 1 plus h plus 8.
Okay, so we have our function up here is defined, right? This is defined in the problem. F of x is square root of x plus 8. So if I ask you, okay, plug in 1, right? Then you're just going to replace the x with 1. If I tell you to plug in, a, you just plug in a, right? If I ask you to plug in a plus h, you're going to just replace the x with a plus h. If I ask you to plug in 1 plus h, you're just going to plug 1 plus h in here, which is what I did there. Does that?
Okay.
Are you sure?
Let me look at it real quick. Okay. Yeah, I think I got it.
If I ask you to plug something into a function, all you're going to do is replace the x's in the function with whatever it is I tell you to plug in, right? If I say, what's f of 2, you replace that with 2. If I say, what's f of 5, you replace that with 5. But if I ask you to plug in 1 plus h, then you've got to replace that x with 1 plus h. And that's what we've done here. We just replaced that x with 1 plus h, and we still had the plus 8.
So, we only let h go to 0 once we've already canceled out one of the extra h's. Is
Yeah.
that the sign that like, all right, let's start putting it there?
You know it's time to actually do the limit once you've eliminated the problem. And the problem is the h in the denominator, because if you let h go to 0, you're going to get division by 0. The only way that goes away is if you actually cancel it. And that's just like in this problem that we did the other way. We didn't do the limit until we were able to get rid of the x minus 1. See, that was the critical step here. This x minus 1, that x minus 1 canceling. See, because when x goes to 1, that would have been 0. But because we canceled it, then in the next step, we don't have the division by 0.
Hey, Professor, why did we say limit goes to 0? So before that, whenever we were doing intervals, whenever they were giving us points, so we would always go with a point, whatever point they have given to the limit, right?
Yeah, that's right. On the other formula, the limit is x is approaching that number. Okay. On the second formula, it will always be h is approaching 0, always.
Okay, got it. That makes sense.
Okay.
Thank you.
How are you feeling?
Doing okay, a little bit better.
Okay, good.
Thank you.
Okay, so let's see. What else do we want to talk about?
Yeah. Question.
Yes.
Whenever we're doing the conjugate, should we mainly use that when there's a square root?
Yes. I would try it when you have a square root. Absolutely. But this is where it's important that you do your homework, because there's all sorts of different problems that require different types of algebra. And there's just no way that I have enough time in one class to go through and show you all the different varieties of algebra you can see. So you need to make sure that you're going through the homework. And then if you're getting stuck, you need to watch my homework solution videos to help guide you through that algebra. All right. I can't tell you, it becomes very disappointing to me when I give a test and I give a homework problem on the test. Like I'll actually give a homework problem, and then the students will not know what to do. And that, I don't know, that either means you're not watching the homework, not doing the homework, or you can't retain any information. I don't know, but it's just disheartening. So at a minimum, you need to be doing your homework. All right. Okay. Now, this thing that we've defined, these two new limits, right? Or these two limits that we have defined over the last two classes, they give you the same answer, all right? But they are so important in this class and in future calculus classes that we have a special name for it. We call it the derivative of the function. So we have this new notation, okay? We have a new notation here. The derivative of a function f at the number a is written this way, f with a little, it's like an apostrophe, but it's really called a prime. It's f prime of a is defined to be that limit, okay? And, or you could define it this way using the other limit. So we have two different limits that we can use. They both mean the same thing, and we call them the derivatives of the function at a. So f prime of a is said to be the derivative of f at a, or you could say it f prime of a. All right, so this is a new definition, new language for us, the derivative of a function at a point a. What I was going to say something about this. So the derivative, the derivative of a function at a is equal to the slope of the tangent line of the function at a. That's what it is. The derivative of a function at a is just the slope of the tangent line at that point a. That's what it is, right? They mean exactly the same thing. It's just new language. Now, let me see if I want to do any of those examples.
I thought
ahead.
that you could write it as what is it, dy over dx? I thought that was
That's coming.
okay.
That's coming. We have that notation. We're not there yet.
Got it.
Okay. Okay, so let's do an example. If f of x equals x raised to the -2, find f prime of a. All right, so what I'm asking you to do is to find the slope of the tangent line to this function at a. Now, have I told you what a is?
I mean,
No,
yeah,
no,
you-
I have not, right? I have
No.
not told you what a is, which means you have to leave a as a variable. Every problem we've done up to this point, I've told you what the a is. I said, okay, a is going to be, 1 or 3 or something. But here, I want us to leave it arbitrary. And this is so important that you understand the difference between this and what we just did. So you have a choice here. We have two definitions. We can use this one. Limit x approaches a of f of x minus f of a over x minus a. Let's call that version 1, v1. Or we could do limit h approaches 0, f of a plus h minus f of a all over h. That's version 2. So let's take a vote. And I know not all of you can vote right now, but let's just say if you want to do the version 1, do yes on the vote. And if you want to do version 2, let's do no. And I'm just going to go with the majority. All right, I think that's good enough. That's good enough.
Can you redact your answer?
Okay, so we have 60% of you want to see the first version. Okay, 60% of you want to see the first version. All right, so let's do that. All right, so I'm going to use this formula. And so here we go. F prime of a should be the limit as x approaches a. And again, I'm not going to be able to replace a with a number. All right, I'm not going to be able to because I'm not given a number. So that means we have to just leave everything the way it is. So let's figure out what's f of x. Do we know what f of x is?
Yeah, isn't that the equation itself?
Yeah, that's just x to the -2, isn't it? Right?
Can't we rewrite that, or do we wait for that?
We can rewrite it. I'll rewrite it in the next step.
Okay.
Now we're going to subtract from that f of a. What's f of a? So what happens when you plug a into this function? You get what?
A to the negative second power?
Yeah, a to the -2. That's what you get, right? And then all of that over x minus a, and there's nothing I can do with that, x minus a. There we go. Okay, now I promise you, if you take this limit right now, you get 0 over 0. It'll be like that every single time. So now we need to do some sort of algebra. And I think this is the point that Danielle is referring to, that it might be easier for us to understand that x to the -2 really means 1 over x squared. And a to the -2 really means 1 over a squared. Do y'all agree with that? That's what negative exponents mean. It means you can drop it down as a positive exponent. Any questions on that? It's just algebra stuff. So no conjugate here, right? Because you don't see any roots. So does anyone have an idea of how we could go about this?
Would you like to have the top have a common denominator first before we do anything at all?
I would like that, actually. And that's what you should be thinking is we have a complex fraction. And so when you have a complex fraction, what you want to do is try and get the numerator together. And so you want to try the numerator fractions together. So you want to get a common denominator. So how about we hit this first fraction with a squared over a squared and hit this fraction with x squared over x squared. And that way they will both have the same denominator, a squared, x squared. And then we can push these two together.
Can we end up factoring out the one of the x and the a's to cancel out with the bottom, or am I just like going too fast in my head?
I don't know if there's such thing as going too fast in your head. Maybe there is, but I think you're working at a good speed. That's good. Let's just put them together first, and I think then everyone can get to that same point. We put this together with this, so we just subtract the numerators. A squared minus x squared is on top, and then when you put these two, same denominator, you just put it on the bottom. Any questions there? So what Danielle is suggesting is that, remember, our problem is the x minus a, right? That's the problem. If we let x go to a, this becomes 0 down here. We want that to go away. We want to be able to cancel it. But Danielle is noticing that up here in blue, that's a difference of squares, right? A squared minus x squared is a difference of squares, so it can be factored. And Danielle, how does that factor?
Doesn't it end up like being x minus a, and then the other part x plus a or something like that?
Careful, yes and no. I mean, it's not x minus a, x plus a, because look at the order that they're in.
Yeah, my bad.
It'll
Yeah.
be
A.
okay, so a minus x and a plus x.
Yes, there we
Yes,
go. My bad.
that's it.
My head just like jumps. So sorry.
It's good. All right, now. Any questions on that step, difference of squares? I haven't called on anybody, but let me do that. Okay, how about, is Claire here?
Yes.
Haven't heard from Claire in a while. How are you, Claire?
Good, you.
I'm good. Good. So Claire, you have any idea what we can do now? We're trying to get rid of this x minus a.
Well, isn't it the top is the same, it's just reversed, right?
Yeah, exactly. So do you remember how we can fix that? Does everyone see that this is almost this, right? Where the hell's my cursor? Okay, this a minus x is almost x minus a. So anyone remember how we can make this x minus a?
Pull out a negative, right?
Pull out a -1. Yeah, we're going to factor a -1 out of this guy right here, and that'll become negative a plus x, like that. So I'm just rewriting this a minus x as -1 times negative a plus x. And if you want, you can rewrite that as x minus a, because the order, you can switch the order and put the x in front of the minus a. And now you can see that those are exactly the same. Claire, does that make sense, Claire?
Yes.
Okay, and now you can cancel them. So we can cancel, but we still have a -1 out there, everyone, so don't forget about that. All right, we're moving here. Limit x approaches a of, let's see, what do we still have on top? We have the -1 we still have an a minus, or sorry, a plus x. And then in the denominator, we have a squared x squared. Okay, I'm just going to highlight everything that was still there. We had the -1, we had that, and we had that. Those are the things that were left after we canceled. Is Ryan here? Ryan?
Ryan or Brian?
Ryan, R-Y-A-N, Medina. I don't see, oh, no, I see. Oh, wait a minute. Did Ryan send me a chat? No, I know Ryan's here. I see Ryan's picture. Oh, well. Okay, let's go with, is Adair here?
Yes, I'm here.
How's it going?
It's going well. How about yourself?
Good. Okay, so at this point, Adair, we've eliminated the problem, right? We've canceled out the thing that gave us division by 0. So how about now, Adair, you just let all your x's turn into a's. Tell me what to write here. I have -1, and then what?
A plus A.
A plus A, and then over
A squared times A squared.
Good. Okay, so let's clean this up. We've got a plus a, right, which is 2 a's, and then times -1. So that's -2a over, now a squared times a squared, you add the exponents. So you get a to the 4th.
A to the 4th.
And then there's one more thing we can do, because we have 4 factors of a in the bottom. We can cancel one of those and make that 4 become a 3. Right?
By canceling that a on top.
Yep, because it's like we have a over a to the 4th. So it's like a over 4 a's being multiplied, and we're canceling one of them. So it leaves us with 3 on the bottom. So -2 over a cubed is our answer. So why is this important? Like what, well, not why is it important, but why would we do that instead of me giving you a problem like, you know, give me the derivative at 4. Wouldn't the derivative at 4 mean that you would find the slope of the tangent line at 4? Right, that's what you would do. You would be finding the slope of the tangent line at 4. And you would have to go through all this work, right, and replace all your a's with 4's. But then what if I came in and I said, all right, now after you've done that, give it to me at 10. And then after you do that, give it to me at 3. And after you do that, give it to me at -2. And I ask you to do like maybe 20 of these. You do not want to have to go through and do this limit 20 times, do you? Right? That would be a lot of work. So what we've done is we've found a general solution for any a. And our answer is a formula that has a in it. So now, if I want to know the slope of the tangent line at 4, I just plug 4 into this. If I want to know the slope of the tangent line at 10, I just plug 10 in here. 3 goes here. -2 goes here. You see, it's like we had to work hard one time, but now we have a general answer. That's much more efficient than doing them individually one at a time. Yes?
Yes.
Okay. All right. Well, let's move on.
Would you say that the first one of the f of x minus f of a is more of like a general formula that you can use with every equation, or is that going to be the h one? Because I thought that one of them will always like be that you can always get the answer with one of those.
No, it's you should be able to get the answer both ways. Just sometimes the algebra is harder in one of them over the other. I was on the fence here on whether or not I should show everyone the other way, but that's going to be another 15 minutes. So I'm like, I don't know. I really don't want to. That's why I had y'all vote. But
We won't do it.
yeah, look, I know no matter what I say that y'all are going to choose to marry one of these. Okay, you're going to like make your commitment, say your vows, and say you're the one for me. All right, I know that's going to happen, but I'm just telling you that you should be open and receptive to using both.
Polygamy?
Right? You should be. What's that?
Polygamy?
Polygamy, yes. I am promoting polygamy here. I can't even say that. It's 2021. I've just lost my job. Thank you, Dan. Okay. All right, so moving on. Sad days, sad times we live in. Okay, so now more about this derivative, all right? We've already said that it represents the slope of the tangent line, right? But more importantly, the derivative stands for something else. And that is not, I mean, geometrically, it's the slope of the tangent line. But in terms of the function, it gives us what's called the instantaneous rate of change of the function at a single point. So I'll go back to when we first motivated this whole idea. If this is, let's say this is time, and let's say this is distance, and you have some graph, then if we were to come to this point right here, A, and we were to find the slope of that tangent line, the slope of that tangent line would be the derivative at A. That's the definition of it. What that's telling you is how fast this thing is changing, the instantaneous rate of change of that function at that point. And when you think about change in this case, here change represents distance over time. Distance over time, and isn't that speed? That's speed, right?
Yeah.
And so this derivative would represent the instantaneous speed of that object at that point in time. And that's what I told you in the very beginning when we were talking about this. We can easily talk about average speeds, but is it ever possible to talk about the speed of something at an instant? Y'all remember me talking about that and saying, is that even possible?
Yes.
Because you have zero distance and zero time, it's division by zero, it's a mess. We have now found a way around that, okay? This is what Isaac Newton and Leibniz were trying to do, is figure out a way around it. But it doesn't just have to be speed. You can have, let's say, I don't know, let's say that this is, and this doesn't always have to be time, but I'll put time here. Let's go time and temperature, okay? So we all dealt with this recently. You know, the temperature in your house over the last week probably looked like that, right?
-0, -1.
So, you know, maybe it was like 74 degrees in your house, and then like last week the power went out and then the temperature started to drop, and I don't know how low it got for you. I was able to run my heater for a while, so the lowest it got for me was 62.
I can see my own breath. Like
What's that?
Like when you I don't know, when you breathe out when it's cold outside and you see like your frosty
You
breath.
can see your breath in your house?
Yeah.
Oh, wow.
Oh my God.
That's no good. So if we were to graph the temperature, what we could do is we go to some point A, and what that would tell us is at that instant, how fast was the temperature dropping, right? It's an instantaneous rate of change. You could do this in chemistry. It could be, you know, something that has to do with a chemical reaction. So you're looking at the instantaneous rate of change of something within the reaction. In physics, it could be something to do with force. And so you're looking at, you know, how rapidly is the force changing at a specific instant. If this is economics, you could be talking about, you know, how quickly your profit was going up or your income was going down. But the key is that we're talking about it at an instant in time as opposed to an average, over an average interval. Okay, so that's very powerful. We'll be able to use that for a lot of things, as you will see later on. So instantaneous rate of change, what I've said here in this note is that if your original function is a curve which gives you linear displacement of an object, that basically means if your function is telling you where you are at every point in time, then the derivative gives you the instantaneous velocity or speed. That's what I just said, right? If you have a position function where you are at every point in time, then the derivative gives you the instantaneous speed. I'm not sure what that is, Brian.
I have a question.
Yeah.
I assume this kind of uses calculus to calculate this, but why can't you simultaneously know speed and position of a particle. Like, I don't know.
Oh,
I kind of don't
Heisenberg-
understand that.
Are you talking about the Heisenberg uncertainty principle, like where you don't know where an electron is?
Yeah, I think so.
Okay, that's different.
Yeah.
Okay, yeah, because we're talking at like the atomic level. Like what he's referring to is that within an atom, the electrons are moving around. And the thing about electrons, they're very hard to figure out because we can only know one of two things at one point in time. We can either know how fast they're moving, but if we know how fast they're moving, we don't know where they are. If we know where they are, we don't know how fast they're moving. And that's called the Heisenberg uncertainty principle. Right, Braxton? That's what you're referring to? So,
Yeah, like, doesn't a lot of like physics use calculus though?
yeah, but that is a very special case when we're talking about electrons. When you're talking about most like particle physics, like not at that atomic level, then we can talk about where something is and its speed at every point in time. See, right now, the way that the state of the world is, the state of humankind is in terms of what we know about the world, is that we have rules for the way things work on a very big scale. So like we know the way planets move. We know that if you drop a rock, off a building, we know how it's going to behave. We have formulas for all that, right? And they work really, really well. And then on the atomic level, like very, very small, we have rules that work there, okay? But the problem is the rules that work for the small aren't the same rules that work for the big. So there's a gap. We don't have, what we're looking for is what's called the unified principle. It's basically the rules that work for both big scale and small scale. And it's eluded us forever for all of mankind. If we could figure that out, then that would be pretty monumental. So I don't know if that addresses your question or not, Braxton, other than to say that, things get weird when they're really small, and just like things get weird when they're really big. You have to remember.
Yeah, that pretty much answers my question.
Yeah, mathematics, what you have to remember about math is that as pure as math is, right? Like 2 + 2 is 4. As pure as it is, we are just trying to model what we see in the world. We take a problem and we try and figure out if there's math that we can associate with that observation. And for the most part, we do a really good job. A lot of our math, just think about the things that we have, right? Just think about what we have right now, right? You pick up your phone, you can talk to someone around another part of the world, right? We're dropping rovers on Mars, right? We're sending color video stream back from Mars. Those are monumental things that we can do, right? And the math is what allows us to do that. But there's still so much we don't know that the math we don't have the math to work it out. So that's why you study. That's why we still need people to think, right? Because we need that next major breakthrough.
I got you. I'll fix it.
All right. Okay, so here we go. We are moving on now to the next section, 2.2. Just so this doesn't get lost, remember that if you know the position of something, then the derivative gives you its velocity, right? So the derivative. Clear your minds for a second, right? Clear your minds for a second. We just had a function, f of x was x to the -2, right? That was the last example we did. And I asked us to find f prime of a. And when we did that, we got -2 over a cubed, right? Now, a is just some point that I would want you to go to on the graph. So whatever this graph looks like, whatever it is, a represented some point I wanted you to go to. And then if you plug that a value into that formula, that's going to spit out the slope of that tangent line, right? That's what it's going to do. All I want you to do right now is just instead of me telling you that that value is going to be A, I just want to call it X instead. All right, I'm just going to call it X. So this formula now changes to f of X, or sorry, f prime of X, and that becomes X cubed on the bottom. So it turns into -2 over X cubed. Right? All I've done is replaced A with X. There's something very subtle about what I just did, but critically important. All right. What we have now is this. We have a function we started with, f of X. And we did something to that function. We took the derivative. And we got this new function. We got a new function, didn't we? And I could actually go graph both of these together on the same graph. And I'm about to do that right now. Okay, so I'm going to go here. I'm going to graph both of these. So first, here's X raised to the -2. Oh, that's not X raised to the -2. That's X raised to the -2. So there is X to the -2. All right. And now I'm going to graph the derivative, -2 over X cubed. All right, that's both of them graphed together. Now, look, I've been teaching this for a long time. This is a very difficult concept for most students, all right? It's one of those light bulb things. It's like once you see it, you're like, ah, I got it now. But until you see it, it's gonna look really weird, all right? So let's do this. I'd like for you to think about, remember the green is the original function and the purple is its derivative. So let's go to the value of 1, okay? Let's go up to the original function right there. And I'm going to ask somebody, how about Emmanuel? Is Emmanuel here?
Hello.
Hey, how's it going?
It's going good.
Good. So at that point that I just went to on the green graph, Emmanuel, would the slope of the tangent line be positive or negative?
It would be positive.
So if I draw a little tangent line going through that little reddish pinkish dot, it would have a pitch that goes up or down. Remember, slopes of tangent lines. Oh, whoa. That's not what I want to do. If I take the slope of a tangent line, like if I ask you, look at that line, does that have a positive slope or a negative slope versus this one? So the one on the left, the slope is what?
That would be negative. Actually,
I think
positive.
you're getting it backwards. Positive is like you're going up as you go from left to right. That's positive slope. Negative slope is when you're going down.
Yeah.
So if I draw a tangent line here, wouldn't the tangent line have to look like this?
Yeah.
Yes. So that slope would be negative, wouldn't it?
Yes.
Okay. Now, is it really steep or is it not that steep? I mean, what do you think?
I'd say it's kind of really steep.
Okay, but it's a negative number, right?
Yes.
It's a negative number. So I would like to now I would like to give that negative value or that negative number a value, and the derivative tells us what it is. In fact, Emmanuel, if you come down here and you look at that point right there, that's the derivative, right? The purple, that value right here, -2, is actually the slope of this line. Okay, so if you look at the green one, you go to 1 and you go to this point and you look at the slope of that line, the derivative function tells you, the y value tells you the slope of that line. So that right there, this purplish, or not purple, reddish line has a slope of -2 according to its derivative. Emmanuel, do you follow that?
Yeah.
Okay, I'm going to stick with you, Emmanuel, just for a moment. Emmanuel, I'm now going to go to 1.5 right here. I'm going to go up here. Tell me about the tangent line there. Is it going to be positive or negative?
I believe it would be the same as the previous, so negative.
It'd be negative, right? But wouldn't it not be as steep?
Not really.
Not as steep, right? Which means it's still a negative number, but not as negative. So if you go to the derivative, do you see this point right here? that value, I don't know what it is, but it's definitely not as much as -2. You following, Emmanuel?
Yeah, yes.
As I move to the right, as I keep on moving to the right and pick points on the original function, do you see that the slopes of those tangent lines are starting to flatten out? They're still negative, but they're starting to get like less steep, right? Does everyone see that? Emmanuel, you're off the hook. Does everyone see that? As I move to the right, these tangent lines, the slope is still negative, but it's getting less steep. I'm going to zoom in because I got to clear all that out of here. So as I start moving, I have a negative slope here. That's this value, that y value. If I come over here, it's negative slope, but it's not as negative. As I come over here, still negative slope. So here's negative, but not as negative. And the further out you go, the slopes of these tangent lines are always negative, but getting smaller. And that's what the purple function's doing. Do y'all see that? I'm getting a bunch of people looking with a glazed look on their face. Okay, I think maybe this one's a little bit too, I think I'm pushing too hard here. Let's do this instead. I'm going to draw a function. All right, here we go. I need to label some things here. 1, 2, -1, -2, -1, -2, 1, and 2. Okay, I'm going to draw a very basic function here. It's going to go like this. It's going to start here. It's going to go up to here. It's going to go over to here. And then it's going to come down to here and stop. Okay, I'm going to call that function f. What I'd like for us to do right now is figure out what the derivative of this looks like. Because the derivative of this function is just a new function, all right? So let me start with Austin. Austin, you there?
Yes, sir.
Okay, Austin. If I were to pick a point, let's say I pick -1, I go up here, right here, and I ask you for the slope of the tangent line at that point. Can you actually tell from looking at this graph what the slope of this little tangent line would be?
It'd be positive, wouldn't it?
It would be positive. Now, can you even tell me what the slope is? Assume that this is a straight line segment from here to here. So can you tell me the slope? Isn't the slope of the orange the same as the slope as of the red?
Yeah. It's
Okay. So what's your rise? And then what's your run here?
slope of 1, right?
It would have a slope of 1. So we go up by 2 and over by 2. Does everyone see that? So Austin, right? Okay, Austin, that means that if I were to graph the derivative, which I'm going to do in purple, I need to put a dot where? At -1, the y value has to be what?
-1.
I thought you said the slope was positive.
Oh, so okay, yeah, then positive. Right? Gotcha. Yeah, I see.
Okay, good. All right, now what I'd like for you to do, Austin, is go, let's say to this point. I'm going to say -0.5. Go up to here and tell me what the slope of the tangent line is here.
1.
It's also 1. So the derivative at that point should also be 1.
Yes.
And how about if I pick a point like over here and I go up here and I look at the slope of tangent line here, Austin, what's the slope here?
Still 1.
Still 1. So the derivative will be 1 here also. In fact, Austin, won't it be 1 everywhere over here to the left?
Yes, until you reach the.
Until you reach 0, right? Until you reach that endpoint. So this right here, this straight little segment from here to here is what the derivative looks like. The derivative of this red function looks like a flat line to the left of, or on the left side of the y-axis. Now, what about?
I have a question.
Yeah.
Real quick, sorry. This may be kind of a dumb question, but is the derivative the inverse of the function, or are those two totally different things?
Yeah, it is not the inverse. Good question, but it is not the inverse. It doesn't undo the original function. That's what inverses do, right? Inverses come in and they undo whatever the function does. The derivative is actually a new function, and it's not related to the original function in any sort of algebraic sense like that. Good question. All right, so how about Gage? Gage, are you there?
Yes, I'm here.
Okay, so Gage, my question for you now, because Austin took care of the left side, what about right here? If I pick this point, plug in here, can you tell me the slope of the tangent line there?
Would it be
Flat, right?
yeah,
Okay, what is the slope of a flat line?
just that number it's at?
No, if you have a line that pitches up,
Oh.
it's positive, right? If it pitches down, it's negative. But what about if
Yes.
it's flat?
0.
0, right? So that means that the derivative at that point needs to be 0. So I'm going to put the derivative right here at 0.
Mhm.
Now, Gage, won't that be the same for any value I pick here?
Yes.
Go up here, flat. Go up here, flat. So that means the derivative will be 0 there, 0 there, 0 there, all the way. From here to here, the derivative is 0.
Yeah.
And let's see. Is Fiona here?
Yes, sir.
All right, Fiona, how about for this next section from here? Like if I go up here, get there and do a slope of a tangent line there, will that be positive or negative?
Negative.
Negative. Okay, can you tell what the slope of that is? Can you tell
2.
what the rise over run is here?
Would it be 2?
So the rise, you go down by 2, right? You go down 2, you go over 1.
Oh yeah, negative.
Negative 2. So that means the derivative, at that point, the derivative has to be negative 2, which is down here. And wouldn't that be the same for every point here, Fiona?
Yes.
No matter where you were. So that means my derivative would be negative 2 all the way, the whole time right there. Okay. Like I said, this is one of those light bulb things. It's either going to like, oh, that makes sense, or like, you're like, what the hell's going on here? All right. So let me just reiterate what we're saying here. If you look at the red function, right? The red function is a function. And the purple is what its derivative looks like. So this, do y'all agree that the purple is a function? Passes the vertical line test? Now it's a step function, it's a piecewise function, but it is a function. For every function, you have a derivative, and that is a new function. We're going to try another one. All right, we're going to try another one because, like I said, until this clicks, until you see it, this is just like a big mystery. All right, this is, let's go with this. This time I'm not going to put anything down here as far as numbers. We're just going to estimate. So I'm going to do this. I'm going to draw. Oh. Okay, I'm going to call that f. That's my function f. Now, what we're interested in doing is figuring out what the derivative looks like. All right, Gene, are you there?
Yep.
All right, Gene. Did I call you already or no? I didn't, right?
Not yet, no.
Okay, Gene. So, Gene, I'd like for you to focus your attention right now on this yellow region. What can you tell me about the slope of the tangent line at any point in that yellow region?
I can tell you that it's negative.
It's negative, right? And won't it be the same at every point there?
Yeah.
Okay, so that means that the derivative has to be a negative value. So I'm just going to pick a negative value down here, and it will. You said it will always be the same, so it'll be the same negative value down here. So, Gene, do you agree that that's a pretty good approximation of what the derivative of this would look like?
Yeah.
Okay, Gene, you did great on that. How about the next section from here to here? What can you tell me about the derivative there?
I can tell you that that one is positive.
would have to be positive, right? So when I graph the derivative, I just need to graph numbers that are positive. So I can put it anywhere, but I'm just going to go from here to here so it doesn't get in the way. So that's just from here to here, okay?
Mhm.
So just in the blue. You want to keep going, Gene?
Yeah, and then negative, and then
So
it would be-
negative from here, like to here, negative again?
yes.
Okay, and then how about here?
I guess that would just flatten out, right? That would just be 0 at that point.
Yeah, so the derivative needs to be 0 the whole time we're in that region. So I need to put my derivative there also, right? They
Mhm.
happen to overlap each other there. And then what? How about on this, Gene? You're doing great.
Yeah, and then negative again.
Okay, so anywhere negative, I'll just put it here. From here to here is negative. And
To
then
positive,
positive, so up here. And then
and then finally negative.
negative again. I'll just throw it right here.
Onto infinity, it looks like.
Onto infinity, yeah. The red is the original function. The purple is what its derivative looks like. I hope that some of you is starting to click. Any questions before I go to another example?
Am I gonna have to use graphs or like when is like on the next test or something like that? Is it gonna be in a graph form or is it gonna?
I will
actually
give
be
you a
written out?
graph and I'll ask you to draw the derivative.
Okay, then never mind.
Just like this. I would give you the red and I ask you to draw the purple.
Is it going to be like similar to this where there's no set values, or just kind of like a mix?
I would give you something where you estimate. So this would be an acceptable answer if someone else did this.
Right, gotcha.
That black would be acceptable too, because it's just that it's negative and positive. Now, let me show you the next one. Next one's going to be a little more challenging. What's that question?
Yes.
Elise?
Yeah. So
What do you got?
so that, like for every like straight diagonal line, the derivative is going to be a straight line.
Are you referring to like, because that arrow, this is an arrow?
No, I'm saying that like, so the original function, the graph of the original function is all just like straight like lines. So for every like straight line segment, is the derivative always going to be like a horizontal line?
Yes, very good. If your graph has a bunch of straight line segments like saw teeth, like teeth on a saw blade, then your derivatives are always going to be little flat little sections. Right? But the thing is, I'm trying to build you up to something. I'm just trying to get you to see this first, because look at this next one, all right? But the answer to your question is yes, that would be the case. But look at this one. Hey, that's like a third degree polynomial, right? Study that in college algebra. All right, so what I'd like for us to think about, I'm going to move my cursor along the curve. And what I want you to be thinking about is at every point, just be thinking, is your derivative positive or negative there? So would the slope of the tangent line be positive or negative? So just don't say anything, just think about it, okay? Okay, now I'm going to go through and I'm going to say what it was. So as we're moving here, the slope anywhere over here, slope of the tangent line is positive. So positive, 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 positive. We get to the top, now our derivative is 0 because it's flat across the top. But then when I move to this side, now my derivative is negative, 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 negative. Till I get to the bottom, now it's 0 again. And then it's positive, 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 right? So we went positive to 0, negative to 0, positive again, right? Agree with that? Anyone have a question on that? Now let's try and graph it, because this is the harder part, graphing it. So I'm going to call on somebody. Is Mustafa here? No? Okay. How about Cody?
I'm here, yes.
Okay, Cody, I'm gonna help walk you through this.
Mhm.
Okay, so I want to start at well, let me ask you, Cody, is there anywhere on this graph where you absolutely know what the derivative's value is? Like for sure, like as a number, you know what it is.
No.
Sure?
I
think
guess
about
at the
it there.
tips they could be whatever numbers at the top, but
I'm asking you, like at this point right here,
Mhm.
what is the slope of the tangent line there, Cody?
Oh, it's 0.
It's 0. So you do know the value of the derivative, don't you?
Yes.
Okay,
Yeah.
so you know it right there. So everyone, we're going to put right on that x value, we're going to put 0. Cody, where else can we do that?
At the other one where it switches sides, right there.
Here. So right here, we know that the derivative's value must also be 0. Okay, good, Cody. All right, Cody, sticking with you here.
Yes.
If I go slightly to the left of that dot, the slope of the tangent line here will be positive or negative?
It'll be positive.
Positive, and I'm going to draw it there. Would you agree, Cody, that that's kind of approximately what it is?
Yes.
That's a positive number. Now, Cody, if I went a little bit further to the left, I'm still going to have positive, right?
Yes.
But is it steeper or less steep?
It's steeper.
It's steeper, and steeper, everyone, means bigger positive, right? So what Cody said was that at this point right here, we got a slope and it was positive. So I would need, the derivative would have to be a positive number. So here's a positive number. But Cody said, if we move a little bit to the left and go to this point, we're still going to have positive, but it's going to be bigger positive. So my derivative should be further up. And Cody, as I keep moving to the left, let me go all the way over here. And I go down here. These are still positive slopes, right?
Yes.
But they're really steep, which means bigger positive number.
Mhm.
So it would be positive numbers up here. And Cody, if I connected those together, don't we get something like that?
Yes.
Does everyone see that? As you move to the left, you get steeper and steeper positive slopes. And the derivative is saying, as you move to the left over here, you get bigger and bigger positive values. The derivative gets bigger and bigger positive here. All right, Cody, good job. Let's move on to Brian. Is Brian here? Hernandez? Yeah, Brian.
Yes, sir.
What was that thing you held up? Should I know that or something?
Oh, those are nail clippers.
Those are what?
Nail clippers.
No, you held up like a sign that said something on it.
Oh, that said stonks. It's just like, it's a funny way of saying stocks.
Sucks?
Stonks.
I'll have
It's a
to
funny way of saying stocks.
Oh, okay, stocks. Got you. Okay, like stock market.
Yeah.
No? Okay. All right, Brian. So I need you to look to the right of this point and tell me right there if the slope of the tangent line is positive or negative.
It's negative.
It's negative, right? Not very steep though, right? Not very steep. And if I go a little bit further to the right,
It's still negative.
slope negative, steeper,
Yes.
steeper, right? And then we get to, I don't know, maybe in here, like, how about this point right here? Oop, I shouldn't do it in purple. Maybe, let me do this. He said, Brian said, here we're gonna have a little negative number, and as we move to the right, it gets more negative. How about if I keep going to the right?
It's still going to be negative.
Still negative. Does it keep going down and get more negative, or does it start coming back up? Think about what's happening to these tangent lines. What are they having to do over here? As they come around that corner, what's happening to their slopes? Steeper or more shallow?
It's getting shallower.
Shallower, which means that they're negative numbers, but they're not as negative, right?
Yes.
So they need to start coming back up towards 0. So if we connect these together, we get this. Natalie, are you live?
Yes, sir.
How's this going for you?
It's going great.
Okay. So what's going to happen over here on the right-hand side of this dot? Tell me about the slopes of the tangent lines.
It's going to become positive.
Positive? Okay, so I'm going to do a little positive number. How about if I keep going to the right?
Still getting positive.
Positive. So steeper or more shallow?
Steeper.
Steeper, which means bigger positive values, right?
Yes.
And so if I connect, oh, geez. If I connect them, I get something like that. So the green is the original function and the purple is its derivative. You're going to need to practice this. There's some problems in the homework that will give you an opportunity to practice this. The way it works, I like the way the homework does it, because what it does is it gives you a bunch of functions and then it gives you a bunch of derivative graphs, and you play like a matching game. Like, oh, this function goes with this derivative and that function goes with that derivative. So you're playing a matching game. See how that goes, but make sure you can do it, because I won't give you a matching game on the test. I'll give you something like this.
So why is, like, I understand that the new function is a derivative and it's just like the instantaneous like slope of the original graph, but like why is it, what would this be used for? Like where would we use this?
Okay, so let me just give you a very quick sort of answer to that. Well, I don't know if I can give you a quick answer. Let me see what I still have to talk about, and then I'll give you an answer dependent upon what I still want to say. So the derivative as a function, notation, that won't take long. Where it's not differentiable, more notation. Okay, so I can cover that pretty quickly in the next class. Okay. You want to know who's asking?
Austin.
Austin. Okay. All right, Austin. I'm gonna answer your question. It's a great question, because at the end of the day, you want to know like when this could actually be used. All right. So I'm going to just give you an example. It's going to take me the rest of class to do this, to set this up. All right. So let's say that, Austin, let's say that we have a road. And let's say that we have a building over here. We'll call it building A. And let's say that this road is, let's say it's a pretty big road. All right. It might not be one lane. It might be a couple of lanes. Let's say it's 50 feet across that road. And we have building A, and over here we have building B. All right. Now let's say that the distance down the road from building A to building B, let's say that that is 200 feet. Now, what we need to do is we need to connect building A and building B together with fiber optic cable, because these two buildings are part of the same company, but they need to have a quicker, internet connection between the two of them. So we need to come in and connect them with fiber optic cable. All right. Now here's the catch. We want everything to be secure. Okay. So everything's got to be buried underground. Got it? It's got to be buried underground. Now, the cost to bury cable. So imagine the different scenarios here. I'm talking to Austin, but I'm talking to everyone. Think of the different scenarios. We could just dig underneath the road and connect them straight line, right? That's one way we could do it. Now, the catch here is that the company that's going to lay the cable charges us a different amount depending on what they have to go under. So if they are just going along the side of the road like this, it's much cheaper than them having to burrow underneath the road, right? Because they have to go deeper and there's certain code, whatever. So the cost is different. And I'm just going to make up a cost here, Austin. Let's say to go under the road is going to cost $400 per linear foot. I'm totally making these up. Okay, these numbers. So if I want to go in the yellow, it's going to cost me $400 per linear foot. Now, if we go on the side of the road, it's not as expensive, and we can do that for $260 per linear foot. Okay? Do you understand that question? Or do you understand the situation? Everyone got that? The question is, how do I do this for the cheapest cost, for the least cost? So find the routing of the cable to get the minimum cost. All right, so we have to talk about cost. All right, let's talk about cost. Now, you may be sitting there right now in your mind saying, there's only two scenarios. We could go straight across like that, or the other scenario is that we go down the road and across. They both have pros and cons, right? If we do the yellow, it's the shortest distance, but it's all the most expensive type of cable, right? Like it's all under the road. Now, if we do the blue, it's longer, but it's, oh, sorry. If we do the blue, then when we get to the green part, that's under the road. So that's gonna be expensive. This is cheap, right? This is all expensive. Understand the two scenarios there? But there's an infinite number of other scenarios. You could have gone, let's say, down the road here and then get to a point and then cut across, right? What we're trying to find is the optimum solution that's going to cost you the least amount of money. So the way we would set this up, I have to get rid of a bunch of this crap. I have to be fast here because I only have 4 minutes. Okay, what we'll do is we'll call this value from here to here X. Okay, that's X. Now, do you all agree that X is the part that's going to be on the side, right? Yes. Okay. Now I need to figure out what this is. I'm going to call it Y, and that's the distance from here to here. Well, I can just draw a right triangle. I have to go fast. I know that this is 50, right? And can anybody tell me what this side is?
X.
Well, X is from here
minus
to
X.
here. Yeah. So if from here to here is 200, then from here to here would be 200 take away X. So that's this side of the triangle. And by the Pythagorean identity, I know that 50 squared plus 200 minus X squared, that's A squared plus B squared, must equal C squared. And so if I solve for Y now, I can take the square root on both sides and I get this. That's what Y is. Y'all still with me? Okay, so what's the cost? The cost of doing this is now a function of X. It is this distance times how much it costs me to go there, right? So it's $260 per foot. So it's $260 times X, that's this part. And then I have to go this distance, which is Y, and that costs me $400. So it's gonna be plus 400 times Y, but Y is this. So Y is the square root of 50 squared plus 200 minus X squared. And that is now a cost function. And what I'd like to know is where the lowest point on that cost function is. Because the lowest point on that cost function is where I'm going to spend the least amount of money, right? So I don't have time. We don't know how to do this yet, but I'm going to type this in here. So I'm going to go, it was 260x plus the square root of 50 squared plus it was 200 minus X and then squared. I believe that was it. Oh, I forgot the 400 in front of it. 400 times. Okay, there it is. Where are you? I got to find the function. Hold on. There it is. Okay, so I need my range to be, looks like to 200,000. So my X needs to be between 0 and 200. And my Y needs to be between there. That'll work. All right, there we go. Okay, do you see this graph, everyone? If we now look, think about X. If we go back to this picture, the biggest that X could ever be would be 200, right? And that would be me going all the way across and then straight over. That's if X was 200. If X was 0, that would be me just doing that. So I need to look at this graph between 0 and 200. If I just look between 0 and 200 and look in here, I'm looking for where the lowest point is on that graph. And this system is very smart. I can probably hover over it and find it. I think that's it right there. Yeah, that's the lowest point right there. Okay, now the lowest point, it's hard to see it here, But the lowest point, let me do one more thing. I'm sorry, I'm keeping you a little bit longer than you want to be here. Let me change this to 12,000. And then make this 1,000. Where'd it go? Shit, I lost it. I lost it. Where's my graph? There it is. Okay, that's more, there we go. Okay, look, now that's the graph, just kind of looks a little different. We're looking between 0 and 200, which is right here. So if you thought it was, hey, just go straight across, you're wrong, okay? Because if I go straight across, it's actually going to cost me roughly $82,000 to do that. If we go all the way down the road and straight across, it's going to cost me about 72,000. But if I go to 157 feet down the road and then cut across, it's going to cost me $67,000. Now, what does that correspond to? What does this point correspond to? Look at the slope of the tangent line there. What's the slope of the tangent line?
0.
0. So the question would be, if we know the function, which we know what this function is, right? We know that function, we just got it. If we could find its derivative and then set it equal to 0, then we would be able to solve this equation and we would get that number. We'd be able to find 157. But we need to be able to find the derivative and then set it equal to 0. Austin, is that convincing enough for you?
Yeah, that makes sense.
Okay. All right. Now we are going to do these problems later. These are called optimization problems, but it's later. We still need a lot of stuff in place first before we can do this. But we're setting the foundation right now. All right, everyone. We have a test on Thursday. Make sure you look at that review. And yeah, I'll see you Thursday. Yeah.
Alrighty then. Bye.
Bye.
Professor.
Have a good one, Danielle. I'll hang out if you have a question. I've got to make it quick though, because I got to be somewhere.
Yes, actually,